Hey, welcome back everybody. We're going to dive into MCMC today. So I've kind of given you the idea of the algorithm. It's basically an algorithm that walks around a space. And it does it in such a way that the positions in space that it takes on, eventually the frequency of that approximates the area under a density curve. So eventually those steps become samples. So and that's kind of the idea. Some of the earlier Monte Carlo stuff that we did, you give it a uniform, you just get a sample back. So this algorithm is more flexible, it works in more cases, but you pay the price in the eventually part of it. So you pay in time. So the samples are not independent of each other, they're Markovian. And so there's kind of an association between these things. They're not IID. But all we really care about is whether or not the frequency of those samples eventually approximates the area in sections of the distribution. So, and if you can do that at any refinement, then the algorithm is officially converged. Now, it never actually fully converges. It gets closer and closer and closer until everything becomes practically useful. So usually you're just going to report things to 1 or 2 decimal places. If you're writing 7 or 8 decimal places in your precision, please stop, unless you're really serious. So do that thing they taught you a long time ago in high school. And any numbers you report should be good numbers. So how do you know that those numbers are reliable? You run your samplers a couple times, and if you keep hitting that decimal place, then you feel pretty good about it. So you could quantify that and say, I need to hit that decimal place, that same number, 95 out of 100 times, and then you feel like you're 95% sure that that number is right. So all that sort of engineering stuff, you could even develop some theory on it and come up with theoretical bounds, but if you do it in a practical sense and you just rerun everything over and over again, I think that that's probably better than the theory. You just pay a price in time for doing it. So I'm going to show you kind of an engineering approach to dissect all this stuff. And we'll get into some theory later, but I want to show you practicalities, how you use this algorithm. And I want to show you in terms of our example that we've been studying. So our example is going to be this. Xi's come from a normal. 2 parameters. We like talking phi now. It's 1 over the variance. And we want to build up a whole bunch of these. So x1 to xn, we'll call that cap x. And we want to build the posterior distribution for these 2 parameters. So we want to learn these jointly. So, want to do joint inference. We can write down this distribution. We could almost write it analytically, but we are going to have gamma functions involved, and that's really just an idea. So you're going to have to approximate those eventually. So even though people might say the kernel of this looks analytical, you don't actually have the full analytical form of the distribution. Question is that important? And to a Bayesian, no. All the part that you need to know about the kernel of the distribution, likelihood times prior, you can write down. So if somebody was doing other inferences, like maybe a classical inferences, maybe you can't always write down the normalizing constants to the sampling distribution, which is an entirely different thing. So our goal is to do inference on these parameters, but we really want to, as Bayesians, we want to think about this distribution, the posterior, which is going to be proportional to the likelihood times the prior. And this is what the whole first part of the class was all about. It's just getting comfortable with these ideas. We can even write down the analytical form of this. This is going to look like phi to the n over 2 minus 1. That minus 1 is coming from the prior, so we're just going to be using our standard prior. Later on, we'll get a technical definition to what a reference prior is. I will point out these are the marginal Jeffreys prior, these are the marginal reference priors. They have this sort of Haar invariance, so location and scale invariance, that's called Haar invariance, those special types of invariant properties. So we don't inject any information about those parameters. And we've even looked at the answers of these, what we get from this solution, at least marginally, and we kind of like the answers. We thought they had nice properties. So S squared was an unbiased estimator, so then we looked at 1 over S squared, that was the expectation of our gamma distribution marginally under all of this for phi, and we thought, oh, that's unbiased too. Did I say anything wrong? Yeah. Just because you take an unbiased estimator and you transform it doesn't mean it's unbiased anymore. So let's get rid of that whole unbiased thing. We don't even hardly care about it. We understand variability of processes, and that has a lot to do with how good our answers are as well. So it turns out it's a very good answer when you account for variance. We're not quite there. We will touch on decision theory later in this class and try to cover all of those bases. But I think what I said is the answers are really good out of this sort of analysis. We can write down the likelihood function. So the likelihood function and the prior together is e to the minus 1/2 sum, here I'll throw my phi up here, phi sum of the xi's minus mu squared, I goes from 1 to n. So our posterior distribution is proportional to that. So in parametric Bayes, which is about what I'm telling you about in this class, you can write this sort of thing down. We've already kind of learned understanding what this looks like and where the area is in here is a hard calculus problem. And so understanding the joint behavior of everything is even harder to understand. But I would say that's what we should be focused on as statisticians. So if you're trying to differentiate to your friends, what does a statistician maybe do, or what does a Bayesian like to think about a lot, that other people doing analytics don't think about so much, it might be the joint association of parameters and how they vary together. And being able to quantify that and make probability statements about how they vary together is probably the goal. So think about neural nets. They don't do that. They just say, here's my net, building some hidden layers, see how well it works, do some cross-validation, do some forecasting and go, oh, okay, it looks like when I see data like this, I expect this to happen. So you haven't done inference. You didn't understand what was driving the whole process. So this is where they will come up with terms like black box. You don't know what's going on. Okay, that was always not the smartest thing to say. It's a regression model. So neural nets are regression models. There's some way to quantify what's going on, which parameters are getting touched most, where are you placing the weights on certain covariates, so on and so forth. There's parameters in the model, just like there are here. And now we have this term, interpretable AI. And it means that there is information in there. It's not a complete black box. This is what people say when they don't want to explain anything. Bayesians up front wants to explain it all from the very get-go. What's the price that they pay? They have to form the likelihood, build their model, do all this other stuff. I'd say there's merit to both. So this was in fashion 10 years ago. Now something else is in fashion, but this is still useful. So later on, people are going to be asking you which data was important in neural networks and what are the driving parameters. They're going to get back to asking science questions. And what does it all mean? And is that correct? And does that make sense? And do I have a scientific understanding of what's going on? This problem is pretty simple. We're just thinking about normally distributed stuff. So maybe you're just thinking about, if I didn't know what the distribution is, maybe I kick in the CLT and do an analysis like this. You don't need CLT because the data was distributed, it's normal. But Bayesians will eventually build up more complicated models. And they will go through this same thing. They'll build up their best model. And at the end of the day, they can't do all the analytical math. They can usually write down what the functions look like. And then they use MCMC to take care of all their integrations. Place the points in space. So it's a very important tool. So I would say this tool alone is what made Bayes popular. So Bayesians were talking for a really long time about doing joint inference, why that's important, and conditioning on sample size and not doing the asymptotic stuff. So those are the important things about Bayes. And it's all very nice as a pipe dream, you know, to philosophize about things, but being able to do it will convince people. So there were a lot of people back in my generation of going through college that would argue about Bayes frequentness. And I'm sure you guys have heard these arguments, but you don't know what they are anymore. So you hear all these people in the halls, oh, he's Bayesian, can't be trusted. Or, oh, it's an asymptotic frequentist. So why do we even listen to that guy? We don't do that anymore. The reason why is we have computers, we can check things, and all our old frequentist friends became Bayesians because of this stuff. MCMC, it's useful, it's convenient, and we'll see some applications where even Bayesians and non-Bayesians can fully agree with each other. Okay, so just to point out, this little c, if you do go to write everything out, if you do write out the words, you're supposed to not capitalize that little c because it's not part of a pronoun. So Markov is a person, Monte Carlo is a place. But if you do use MCMC and you're just talking about it and you're initializing and saying it that way, you're allowed to write M capital, C capital, M capital, C capital. But if you write out the word and you lowercase the c, you should lowercase that c. So just some extras about this. Hopefully everybody understands that part. So I gave you a presentation the other day on Markov chain Monte Carlo, and I wrote down some rules, and I said something about there's 2 steps: you propose and then you accept. Let me write down what that rule is on the chalkboard in terms of this problem. Later we'll study the code that we've written down. How many people do we have? I think I'm ready to give you a gift. I said if it was over 15 in my mind, and we're way over, then I will establish a gift today. So I'm going to just make a note. Note, midterm will be take home. More on that later. I'll give you the full instruction set on Friday. But the idea is I'm going to send it to you on Monday morning, and you'll return it to me about 5 p.m. on Monday night. So I'll give you a few extra hours to do everything. It's not meant to be brutal, so you will be able to use your notes and all of that for doing the midterm. So I know we're budging and give stick with all of this material. So there's a lot to take in, so now you can at least do it in a relaxed way and actually learn something.
When is the homework free to return?
I think the same day. So I'm thinking you'll turn that in also. Now I might have to omit a problem. So
for the take home, I like the midterm analysis take home. Are you including like coding problems?
No, I won't do that. Okay. So I'm not going to change the structure of the exam and soak up your whole day. It's intended to take an hour. So if you were fast and it's studied, you know, you'd be that person at the end, let's try to still do 15 minutes of work in 3 seconds. You know, so it might take you 2 hours to get through it. I would say watch that, how long it takes you, and maybe tell me how long it takes you so I have some idea. So I wouldn't mind knowing just for trivia's sake. Okay, we'll go through all of this. So now that everybody's awake, so we'll go through the rules later, so we'll revise, and I'll look at that homework 3 and see if there's anything we need to omit. Keep in mind on Thursday we have a review session, so there's still plenty of time to be thinking about all this stuff. Okay, so let me write this down in kind of a Gibbs sampling format. So this is the way my code works. So my code works like this. I have a for loop. I'm going to index everything by t for time. And I'm going to sample from 2 different distributions. I'm going to first sample from mu. This is going to be coming from its marginal distribution, or its full conditional distribution. It's different. It's going to be conditioned on phi, t minus 1. So I'll need to initialize phi 0. And you would initialize that outside of the loop. So you're going to need to do that initialization. We know what distribution this is. This is a normal distribution. So you would sample the mu's from that. We wrote that down last week. And then I would update my phi. Technically, this can all be done because that's a gamma distribution. We've already done the math to figure out what gamma distribution that was. That was about week 2 or 3. We went through that. This was our first example in class. This was our second example in class. This is called a Gibbs sampler. So what I'm going to do in my code is I don't exactly do this. I don't take advantage of I know what those distributions are. So I actually approximate this. With Metropolis-Hastings. I need to tell you what that is. And I also approximate this one with a Metropolis-Hastings step. And the reason I do this is to slow down the code and try to teach you 2 things simultaneously. People often do things like this, where they'll break up their distribution into the full conditionals. Nothing easier to write down than full conditionals, because you don't have to integrate. There's no math. You're just conditioning on all the old parameters. I want to remind you that the conditional distributions have information about the joint. So these are just the slices through the joint distribution. And if I account for all the slices through the joint distribution, then it makes sense that I've at least understood what the joint relationship is. So this is called Gibbs sampling. If you know how to sample from the full conditional distributions, let's say you have 3 parameters, you can write down 3 full conditional distributions and do the same sort of thing. If you know how to do that, you don't need Metropolis-Hastings. So Metropolis-Hastings slows everything down typically further, but it's not always the case. So if you have block updating that has covariance in it, so if these parameters were associated, let's just draw a picture of a downside to Gibbs sampling where Metropolis-Hastings can actually help you. So this is just a side, a general statement. So a side, this is when MH is better than Gibbs. Sometimes people think Gibbs is better because there's no acceptance probabilities. The acceptance probabilities are 1. And in fact, we can show that Gibbs samplers using the full conditionals have an acceptance probability of 1 in the Metropolis-Hastings decision rule. We'll look at that in a minute. I haven't written it down. But if I had 2 parameters, let's just say they look like theta 1 and theta 2 that I was sampling. The reason I don't want to write mu and phi is they don't look like this in this actual example. Where you remember what they look like, they look triangular. So they're not correlated with each other. They're associated, but they're not correlated. If you fit a regression line through its points, it would be a flat line. Pull towards the bottom, because there's more points down there. So let's say the posterior distribution looked like this for theta 1 and theta 2. So we're going to be thinking about this posterior distribution. I built something up. It's got 2 parameters in here. This is the picture you would always like to see in advance, but you can't. So usually you have to run samplers that are clunking around in converging slowly, and then you get some semblance of an idea of what the posterior looks like, and then you go, oh, I can adapt and build a better proposal. I'll tell you more about this later on, how you actually do this in practice, but let's just say these were really tight with each other. So this is supposed to be a 2-dimensional distribution representing this out of the board. We can make it even tighter. So I'll make it really tight right here. It could be even tighter. But just think about what a Gibbs sampler would do. The Gibbs for this would look something like this. First, your updates would be pi theta 1 given x and theta 2. You would base it off of this distribution, and then you would sample the other parameter conditional on the first. So you would index these things. This would be based off of t minus 1, and this would be your new sample. So theta 1 t would come out of here, get plugged in here, you get a theta 2 t out of this distribution, and you plug that thing back around in a for loop. So what does that look like visually? That means that if I'm going to sample theta 1 given a theta 2, so let's say theta 2 was somewhere, so I'm going to say it's here. Let's say that was my initial value. Now I'm being really optimistic because I placed it right in the mass of the distribution. So even that won't help you. So this is even worse if I had started it way out there. But even if I did this, where I could sample theta 1 from in this direction would be along that stripe right there, that band, because it has to be conditional on where theta 2 is. So those are all going through the same point, theta 2 right here. Let's say I pick this point right here for theta 1. So now I have that point. So now the only stripe I can really sample from is in this direction. So then let's say I grab this one, then I can sample in that direction. Then let's say I sample in that direction right there. Let's say I pick that one. I do the same thing over and over and over again. And then eventually I learn about this part of the tail. Now I gotta come over here and learn about this stuff over here. And it's gonna take a long time to get there. So, and if I made this really tight, it would take a long time of being able to jig and jag to get down to this part of the tail space. So breaking things out into full conditionals isn't a great idea if those parameters are tightly correlated. What you might want to do is block them together and update them together and have a proposal that knows where the correlated directions are. So you might want to block update those parameters. So let's imagine I had a theta 3, a theta 1 and a theta 2. Theta 1 and theta 2 were tightly coupled, and theta 3 was not tightly coupled with theta 1 and theta 2. I could update theta 3 on its own, and I could block, that's a word that everybody uses, theta 1 and theta 2, and use a proposal to search around that direction. And that will march you back and forth as fast as possible. So what I would want is a proposal to actually bounce me in these directions so that I can learn about here and then jump over here. So an MCMC or any sampling technique that has a dependence between the sampling, what we like to think about is how fast it mixes. So everything on the chalkboard I show you doesn't really tell you about that. When you code this up and run it on your computer and see that it takes hours sometimes for things to converge, you'll start to appreciate the theory. Okay, so let me tell you what Metropolis-Hastings is. So this is going to be a block updated Metropolis-Hastings. I'm going to write it out in terms of this example right here using the exact same example. So block updated Metropolis-Hastings. Let me first write it down generically with theta 1 and theta 2. And then I'll write it down fully with mu and phi, and you can see what I've encoded. So aside, this is in general, we're going to try to sample from pi theta x, this thing. So this is the name of the game. So Bayesian, it's not the only one that can use Metropolis-Hastings. It's just a search algorithm that samples from things. Anybody could use this on any function that they wanted, so long as it was positive. you're integrating. If it's not positive, throw a negative sign in front of it. Flip it upside down and treat it differently in that region. So sample from this thing right here. This is for block sampling. I'm going to do all the work all at once. So this looks like this. It runs in a for loop. He goes from 1 to some big number. So usually we crank that number really high. Back in the day, it would be like you'd have to wait a long time to sample, you know, 1,000 uniforms. Nowadays, we can have those like that. So I'm not going to dwell on how big that should be. It should be big enough. So if all of a sudden you're trying to approximate a mean or something like that, or a variance, or understand something, it should be big enough that your numerical precision that you're reporting is reliable. So this looks like this. There's 2 steps. You're going to propose. And then you're going to accept. Conceptually pretty easy. So we're going to propose theta star from some proposal distribution. Okay, I'm going to let this proposal be Markovian in some sense, because I'm allowed to do that. This is Metropolis-Hastings. There is another algorithm, Metropolis, and I'll explain it after explaining Metropolis-Hastings to you, because it's a subset of that algorithm. So this is my proposal. Let me give you an example. So say that theta lived between minus infinity and infinity. Okay, this could be in high dimensions, and I could do it in R cross R cross R cross R as many times as you would like. Let's just do it in R. You have no lack of understanding of how this works in one dimension, but if you'd like to think about this in a high dimensional space, you can. So my proposal, just so I can write down an actual example, might be this. Normal theta t minus 1 with some tuning variance. So what that means is I'm going to search around where I was last time, and I'm going to gauge how cautious I'm going to be by specifying psi. So if I felt really ambitious, I could make that big. If I wanted to tippy-toe, I could make that small. And we'll talk about the trade-off between both of those ideas. So this is some proposal distribution. This is the local proposal. So here's our acceptance probability. This looks like the minimum between 1 pi theta star given x compared to pi theta t minus 1 given x. I'm writing it down just a little bit differently than the way that I wrote it. Well, actually, I'll write it exactly the same way that I wrote it in the notes. This looks like g theta star given theta t minus 1, g theta t minus 1 theta star. So that's the acceptance probability. We'll talk about that acceptance probability. I love this acceptance probability. It's taught me more about life than anything else in all of statistics. So hopefully you get as much out of it as I do. Let me just write in this last little bit. What we're going to do is we're going to flip a coin with this number right here. I just want to point out the number is bounded by 1. And it's positive. Everything in here is a positive quantity. So this is a number that lives between 0 and 1. So alpha, we can interpret it as a probability and flip a coin with that probability. So what I'm going to do for theta t is I'm either going to take theta star or theta t minus 1. So this is where we were last time. So just to point out, we don't reject anything in this algorithm. We always store something at every step, and if we've stayed at theta t minus 1, there's at least evidence to suggest it's a high probability point compared to where you're proposing. So this happens with probability alpha. This happens with probability 1 minus alpha. So it's just a Bernoulli coin flip. You're going to get one of two realizations. So that's Metropolis-Hastings. Let me write down this rule just a little bit differently. I'm going to write it down like this. Same rule, same thing. I sometimes like to think about it in two different ways depending on what I want to explain. The thing I want to point out is that's an importance ratio. So the same thing that we saw in importance sampling, and I called it the important weight or the important ratio there. I want to point out in Monte Carlo, anytime you propose, because you can't sample from the true target, but you can propose something that lives in the same space or at least an expanded space. It can't be any smaller than what you're trying to sample from, but it could be bigger. If you make it bigger and the support lives outside, this would be a 0 right here, and you would just reject that sample, so you probably wouldn't want to make something too big. So these are importance ratios right here. This is the importance ratio, the ratio of importance ratios. That's what I'd like to point out. These go together. That one goes together here. So keep in mind, this is a density on that. That's the random variable. This is just fixed. So does everybody at least understand what the algo says? Anytime I try to understand anything or prove anything, I make sure I understand what it says first. So I make sure I understand what the idea is. I could code this up. Could anybody not code this up? If I gave you a likelihood and prior that you could write down? Any obstacles?
Probably take me a hot minute.
Hot minute, okay.
You'd have to be able to sample from the proposal history. We're assuming.
Yeah, I'm assuming that. So if you can't sample from the proposal, it's not a proposal for you. So you got to be able to sample from that. Good point. But you could kind of imagine this could be pretty complicated. But that's a simple idea. So we know how to sample from normals. We discussed it last week. So we're going to use structures that we know how to sample from. We could sample from Cauchy, their heavy tail. That's pretty cool. We know how to do that. Now if we can sample from a gamma and a normal, we can sample from a Cauchy. What about this? Do I need to come up with the integrating constants for this? Do I actually need to write down this thing? Likelihood times prior. So do I have to do any math up front? Didn't I say this is like integration free? Somebody tell me the obvious thing.
Generalizing constant doesn't depend on theta, so it's just you can't plot.
Yeah, this is not a function of theta. This is a function of x. So I've integrated over all of theta. So you can write them in if you want, or you can take them out, but they cancel each other because it's the exact same constant right here. So I could replace this and write it like this. This is how I probably code it up, or at least in spirit I would code it up this way. Just keep in mind, I'll do it on the log scale every time. So unless I'm in class trying to show you what could go wrong. So this would be the likelihood star given x compared to the likelihood of where we were last time, t minus 1 given x times my prior, we'll call that pi theta star, compared to where I was last time. And then I'll come up with the inverse ratio of the proposals. Theta t minus 1, g theta t minus 1, given theta star. So that's what we would code up, and it would take now a half a hot minute to code this thing up, because you don't have to do any integrations. You just write down the likelihood function, write down the prior. You could even multiply them together. When I multiplied them for our example, I didn't multiply anything. I just took that phi inverse and drug it into the exponent. So I would encourage you is to do the simplest algebra you can think of that doesn't include products to write this thing down. That is the entire field of numerical analysis. So not exactly, but that's at least the idea, is make sure the number of calculations you do is minimized and make sure they're all stabilized. And I'll walk you through some exercises like that. Okay, so now let's just talk about how we extend this to our block updated MH, and we're going to be trying to sample mu in phi. So we want to collect a bunch of these samples. For t goes from 1 to tau t, what I'm going to do is I'm going to first propose a phi right here. I'm going to call it g phi. And I'm going to propose a mu. Let me just ask, just real quickly, because this is the name of the game. So all Metropolis-Hastings samplers, let me put an asterisk on that, because it's like everything else in the world. There are subcategories out there that don't cleanly fall into this box, but they're very inspired by it. So all asterisks, all MCMC algorithms are Metropolis-Hastings in disguise. It's almost true. So ensemble samplers don't fall into that category always, and I've invented one myself that doesn't exactly fall into this, but it's very close. So it's not like I wasn't thinking about exactly the theory of Metropolis-Hastings when I came up with everything. So I'm going to jointly propose this. I could come up with joint structure to propose this, but I wouldn't know how to do that. We've already had this whole conversation. So I don't know what the joint structure is of the target. If I kind of understood that triangular shape really well and knew how to sample from it, I could probably sample from the target. So I actually have no idea how to jointly do this, so I'm going to independently propose it, and I think we've already gotten our heads around that. Kind of makes sense. We came through this line of thinking when we developed our priors. So what would you pick here? Maybe, just as a candidate, this gamma. Good choice. Some gamma right here. If you actually use the full conditional distribution, your acceptance rate will be 1 on that. That'll be kind of cool. So you might not know exactly which gamma, but at least you didn't say, you know, T or something that places negative mass. Half your samples would always be a waste of time. They would have 0 contribution in the likelihood function. You'd need to put an indicator on your likelihood to make sure you're controlling the bounds of support. If I threw a negative sample into the likelihood and I didn't say that had 0 likelihood and I just plugged it into the function, the sampler would go berserk. You'd be chasing your tail for 2 weeks, trying to figure out what your error is, and then you would have that, oh no, I just wasted a lot of time being silly. So don't throw negative stuff into your likelihood function unless you have an indicator built in. Usually in our code, we don't do that. So usually we know we're throwing in the right thing so we don't have to check it. I will point out, I always rewrite my normal functions in high dimensional space. I don't use the built-in ones in MATLAB or R because they always check to see if the matrix is positive definite. And so if I do things to always make sure everything is positive definite, I can omit that step. So sometimes knowing what you're feeding in is important. So maybe some sort of a gamma, or maybe a truncated normal. So, or truncated normal. That could work. I will point out that Darren Wilkinson's blog that I have a link on the webpage to discusses these choices. And I'd like you to look at them because they'll help you to do your homework. If you read that page up front and spend the 15 minutes looking over it, your homework's like this. So if you don't, and you do it in the other way, maybe you learn more, but it'll take you more time too. So nothing wrong with either order, but if you do it one way, it'll feel painless. I don't know if that's a good thing. I always remember the things that I struggled with the most. Okay, so I've got proposals. What about this one? Maybe just that, right? I don't need to know anything. I'll just use this one. And then I'll kind of wiggle that thing around. And if I pick a variance that's close to how much variability there is in that direction, it'll accept really nicely. If I tippy toe really small, my acceptance rates might go really high. So I want you to just look at this right here. If my proposal step is really tiny, then wherever I was last time, that's probably really close to it. So if I'm thinking very generally that I've got a local proposal right here and this thing is small, then these are probably close to 1 right here. If I actually use a normal, this format right here, this ratio is 1. Let me just write that down. Let me show you that. G theta star, given theta t minus 1, over, this is actually the other way around. That's why I always say inverse ratio of proposals. Theta star divided by G theta star, theta t minus 1 is equal to e to the minus 1/2 theta t minus 1 minus theta star squared over phi. So I call that variance to begin with. So I'll write it in that way. E to the minus 1/2 theta star minus theta t minus 1 over phi. Square that. So if I reverse the order, I just change the sign, it's exactly the same function. You could write in your normalizing constant if you want, but it really is a constant at every step. It's 1 over square root 2 pi square root of phi.
So is that property true for any proposal distribution that's symmetric around it?
Yeah, so that's what we call it, is if you can change the arguments and it's the exact same function, the proposal is called symmetric. Just keep in mind, visually, that doesn't need to mean symmetric. So even normal distributions where you're block updating things in high dimensional space, I'll think about 2-dimensional space. So I have this oval here, it's not symmetric per se. It's like reflected and turned around the origin, but I assure you that function is symmetric, meaning if you interchange the mean and the random variable in both directions, it's exactly the same function. So I'll say this without any big wow. When you use a symmetric proposal that has this property, that this thing is 1, that's called the Metropolis algorithm. Hastings, 3 years after Metropolis wrote down his paper, said you can make a correction and use any old proposal. So that's Markovian. And as long as you include it like this. So, and how do you include it? Through the importance ratios. So anywhere I see its target function, I divide by its proposal function. So yeah, you could do that. So this might be your local normal. Leland Wilkinson's paper says instead of working with phi, work with log phi. transform that random variable. Now you do need to take a Jacobian up front and do a little bit of math, but it's not that hard because you know how to take the derivative of log phi. So you have that extra -1 sitting out there in front of somewhere. So derivative of log phi is 1 over phi. So if you do that, then you can use the local normal proposal, because log phi lives between -infinity and infinity. So sometimes transforming the problem can lead to you using a simpler proposal. So lots of strategies, that's what Darren talks about here. So he writes out that whole conversation, shows you some simulation. And in the simulation that I have up on the website, it actually makes the error assuming that the local normal is symmetric, and it's not. It's integrating constant changes at every step depending on how much you have to shift that normal. So when you truncate the normal by 0, you have a different amount of mass over to the right-hand side of things depending. So you have to change that normalizing constant. So that's just a heads up of something that's on the homework. So then what you just do is you write down your acceptance probability, min. I'm going to take my likelihood function. So I'm just going to write down this whole thing, my posterior. This is going to be phi star to the n over 2 minus 1. E, I'm going to have two ratios that I'm going to fill in right here. So e to the minus phi star over 2 sum. I goes from 1 to n. This is going to be our xi's minus mu star squared. Let me make that cleaner. That says phi star. There's going to be something really similar down here. Phi to the t minus 1, where we were last time, to the n over 2 minus 1. E to the minus phi to the t minus 1 over 2. Sum xi's minus mu t minus 1. That's right. Squared. I goes from 1 to n. And then I'm going to multiply this by g. I'll do it down here first. Phi star given phi t minus 1. G mu star given mu t minus 1. This is g mu t minus 1 given mu star. This is g phi t minus 1 given phi star. So depending on what you pick for your proposals, you'll need to include their PDFs right there. I didn't write down any normalizing constants right here because they all cancel each other. I didn't try to integrate anything up front. So this is just the likelihood function evaluated at theta star upstairs. And this is the likelihood function evaluated at theta t minus 1, where theta is mu and phi. This is the inverse ratio of the proposals. So that's all you're coding up right here. So all you need is some sort of a joint structure to propose in. And then we'll just end the loop and we'll update mu t and phi t. So I'm going to flip a coin with that probability right here. Plug in the 1 right there so it's not just the min with itself. So we'll truncate it there. We'll flip a coin with that probability. If it lands heads, we'll update these with the proposed values. If it lands tails, we'll update it with the old values. So there's only 2 sets of values. What I've done here in my code, and we'll start next time with it, is I did an MH step just right here. And I did an MH step after that. So I first proposed mu, then I decided to accept it conditional on where phi was. And then in this step, I proposed phi, and I did an MH step with this being the target. right there. So I incorporated both ideas. We'll look at that, and that's what's coded up online. The reason I do that is because they're not hyper-correlated with each other, so I probably don't need to block up data. So I can break them apart, and that's probably a good idea. And the reason I used an MH step instead of just Gibbs sampling is so that the conversions would slow down slow enough that I could talk about things in between and show you what the behavior is you'll expect to find on difficult problems. I want to just point out one more thing that we'll talk about when we come back. We'll write this down. But I want to just say something about this right here. So if your target has a higher density, so if this thing is bigger than that, you're inclined to accept. And that kind of makes sense. So if I'm moving to somewhere that has higher mass, I should probably accept making that move. So that means that this density would be bigger than that one. So it lives in a region where the area around it is a little bit bigger. So you probably move to that part. But be careful when you do it. Make sure you're welcome to move back. So you have to think about your proposal structure. So what this says is if moving back to the old location is unlikely, meaning that that's going to be small compared to this, then maybe not make the move. So this is a don't burn your bridges philosophy. So you might say, oh, that looks really attractive. I'm going to go take it. And that sounds great. But once I make that move, I'm not welcome home anymore. So be careful with that sort of stuff. We confront those ideas in life all the time. And I really think about all the time, what is my proposal? My life proposal. So I could get really ambitious and throw points around everywhere, but sometimes I want to stay about where I'm at. So come back next time, think about this algorithm, talk about these two incarnations of the algorithm, and then on homework you'll be playing around with these two things. So at least you know what the block sampler is and the sequential sampler. Block sampling is where you propose everything together and you accept them as a group, a block. Sequential sampling would be like doing the acceptance on that and then doing the acceptance on that. So there would be two separate decisions instead of a group decision. Okay. I'll see you guys next time. And we will pick up with the code, see it run, move around some toggles, talk about a little bit more theory, but mostly practical stuff. Hopefully that'll get you ready to do your homework. And then on Thursday, we'll have a review. You guys are really stuck. Thanks, you guys.